Today I have 5 problems for u-substitution integration to work through, to learn how to do it, and to practice with a bit more difficult problems. Our first problem is the integral of 2x times e to the 3x squared. And our first step here is we're going to be finding what to use as u. So u-substitution is kind of the opposite of chain rule. So what we want to find is that inner function similar to the inner function from chain rule. Here, we really want to look at the 3x squared that is in the exponent of e and set that equal to u. Our next step is going to be solving for the derivative, which is also going to be du over dx. Here we get du over dx equals 6x. And now what we want to do is we want to find um, a function for dx because we will then be able to substitute that in for this dx and change our integration term from x to u. So we can rearrange du over dx equals 6x to get du over 6x equals dx. Now we are going to take du over 6x and plug this in for dx in the problem. This is our second step, and we are going to get 2xe. We are also going to plug in u for 3x squared. So if you see a 3x squared, just plug in u, which is going to be in the exponent for e. And then, of course, we have to plug in du over 6x. And we can cancel out terms. Hopefully, all of the x's should cancel out. That's how you know you did it correctly. And they do here. Then we're left with a 2 over 6, which we can move to the front. So we have the 2 over 6 times the integral of e to the u du. Now, all we're going to do is we're going to integrate this in terms of u, and we're going to get 2 over 6 e to the u plus c. Finally, as our last step, we're going to plug in 3x squared back in for u to get 2 over 6 e to the 3x squared plus c as our final answer. So our first step is going to be finding u and finding dx. Next, we plug in what we have for dx in order to get rid of all the x's. Third, we're going to integrate in terms of u. And then fourth, we're going to bring back our term for u and plug it back in and get our final answer. Let's look at our next problem, which is going to be a definite integral. So we're integrating from 0 to 2. And this is very similar. The only difference is now we are going to be changing our bounds of integration as well. So, like the first one, we want to look at the inside function. This is similar to the inside function in chain rule, which is going to be this 2x plus 1. We set this equal to u, and we find the derivative, du over dx equals 2. We can rearrange to solve for dx, and we get dx equals du over 2. Next, we're going to plug in du over 2 for dx because they are equal, and we will get u to the 3 times du over 2. Now, for our bounds of integration, these are also going to change because we are now working in terms of u rather than x. To find the new bounds of integration, all we're going to do is we're going to go back up to our u equals 2x plus 1 and plug in our a and b values for x. So we get u1 equals 2 times 0 plus 1 equals 1. And our second bound, our upper bound, is going to be 2 times 2 plus 1 equals 5. So this 0 is coming from our a, and this 2 is coming from our b in our original definite integral. And now we have our a is going to be 1, our lower bound, and our upper bound is going to be 5. So we're integrating from 1 to 5. It's very important that you change the bounds of integration when you are doing this, because if you keep 0 to 2, then it's going to be wrong. Finally, we can evaluate this integral, which is 1 over 2, the definite integral from 1 to 5 of u to the third du, which is going to be equal to 1 over 2 times u to the fourth over 4 evaluated at 5 minus 1. You can switch it back to 2x plus 1 for u and change back the bounds of integration here as well, but I prefer to keep it in u and these bounds because I think it is easier. Next, we are going to solve for it, and we're going to get 1 over 2 times 5 to the fourth over 4 minus 5 to the 1 over 4, which should come out to, so 5 to the fourth should be 625. So 1 over 2 times 625 over 4. Let me move this down. So 1 over 2 times 625 over 4 minus 5 over 4 equals 1 over 2 times 620 over 4 equals 620 over 8. And I'm not worried about rounding, and neither should you. And this is going to be our final answer to this problem. Our next problem, x times cosine x squared. This one, we don't need to change the bounds of integration, making it nice and easy. So our first step is going to be finding the u. Again, we're looking at the inside of the function. Here it's going to be x squared, which is inside of cosine. And we're going to find du over dx, or the derivative. Rearranging for dx, we get du over 2x, and we're going to plug that in for dx. We get x times cosine of u. So we set u equal to x squared, which means that we can change x squared to u. And we multiply this by du over 2x. We know this worked because an x at the top and the bottom cancels out, and we're left with no more x's in the integral. Moving the 1 over 2 to the front, we get 1 over 2 cosine u du, which we can simply evaluate and get 1 over 2 times, this is going to be positive sine of u plus c. And now we plug x squared back in for u, get 1 over 2 sine x squared plus c as our final answer. All right, another definite integral. We're taking the integral from 1 to 4 of x over square root of x squared plus 1. This one might be a bit more confusing on what is going to be our u, but we want to look at the inside of the function, which is going to be x squared plus 1 inside of the square root. So our first step, u equals x squared plus 1, and we want to find its derivative. Next, we solve for dx, and we're going to plug in du over 2x for dx. And we're also going to plug in u for x squared plus 1. That gives us x over square root of u times du over 2x. And we do need to change our bounds of integration. So our lower bound, if we plug in 1 for x into x squared plus 1, we get 1 squared plus 1 equals 2. And our upper bound is going to be 4 squared plus 1 equals 17. So now we are taking the definite integral from 2 to 17. And we also get to cancel out an x at the top of the in the top and the bottom. We're left with 1 over 2 times 2 to 17 of 1 over square root of u, which is also 1 over u to the 1/2. Using exponent rules, we can bring it to the front and or bring it to the top and add a negative exponent to get u to the negative 1 over 2 du. Now we can just apply the reverse power rule. We get 1 over 2 times the integral of u to the negative 1 over 2. So we're going to add 1 to the exponent and get u to the 1/2. And then we're going to divide by that new exponent. So dividing by 1/2 will give us 2. Evaluated from 2 to 17. And our 1/2 in the front and our 2 connected to the u to the 1/2 can cancel out. And we're left with square root of 17 minus square root of 2 as our final answer. Okay, let's get to our final problem now, which is sine, and then inside of the sine is ln of x over x. So this one might look hard, but if we stay true to our process, we can figure it out. Our first step is finding u, and again, we're going to use the inside of the function. Now, you might be inclined to use the inside of natural log, but here we want to use the inside of sine, which means that u is going to be equal to ln of x, taking the derivative, du over dx equals 1 over x, and if we rearrange to solve for dx, we get x times du. Then we plug things back into our original equation. Plugging in u for ln of x, we get sine of u over x. And then plugging in x du for dx, we get x times du. The x on the top and the bottom cancel out, and we're just left with the integral of sine of u du, which is equal to negative cosine of u plus c. And our final step, plug in ln of x back in for u. Negative cosine ln of x plus c is our final answer here. Let me know in the comments if you have any other questions or if there are any other topics you want to go over. Thank you.